So I'm Scott Shadley. I'm with Solid Dime, much to the chagrin of Mr. Leonetti in the front row here. I'm going to be co-presenting today with Andy Banta from Ignition.
Hey, and I am Andy Banta from Ignition, and it's time for you to actually listen to us and not listen to each other.
Oh, that's so
no.
mean. That's so mean.
No, I know. And we're here to talk to you about the total cost and performance of SSDs. Or maybe not. Scott and I started talking about what we wanted to discuss with the total cost and performance of SSDs, and we realized that what we really want to talk to you about is you're not paying attention to the right thing. And so let's actually talk about not paying attention to the right thing, where there's an awful lot of people who go off and purchase disk or storage or SSD based entirely on cost per gigabyte. And that's not necessarily the way that you want to use SSDs, or possibly you're buying it by the throughput or IOPS on it as well.
Yeah, and you'll see people trying to think about which PCI interface do I need, and am I the bestest to the fastest or the worstest? And those topics just don't tend to help with solving the actual problem that you're looking for when it comes to putting out dollars to make the solutions work the proper way.
Yeah, and I mean, another big part of it is that if you're just looking at the specs, if you're just looking at the throughput or the IOPS or the capacity or some combination of them, you're not really paying attention to what your workload is. And that is what you're actually trying to satisfy. You're trying to make sure that your workload can get the storage that it needs at the speed that it needs and in the right mix of things that it needs. Where if you're just measuring throughput or IOPS, you really aren't taking into account any of the contention or anything like that.
And FIO is not your best friend.
Yeah, FIO is definitely not your best friend at times. And by the way, if you're paying attention to the slide, don't pay attention to that. Listen to us. You're paying attention to the wrong thing if you're reading the slide.
It's 11:30 on a Monday morning. We thought we'd mix it up and see if you guys could pay attention.
Yeah, right. Yes. So the slide is nonsense on purpose. It means nothing. Listen to what we're saying.
Yeah. And so as we move forward with that, and you look at what we put up on the next slide, again, it comes back to what are you hearing in the market, what are you understanding from the marketplace, and what it really means to you when it comes to deploying real solutions, moving them forward. So you can make a lot of noise, and you can put anything you want to in a press release. Trust me, I was at a startup or two. I've done that myself. But when it comes down to it, it really matters around cost, workload management, things like that. Deployments of solutions are what are valuable. Understanding how other people are using the technology, what you can do with it, how you can leverage it, are as important, if not more important, than just what someone says in a press release. So I had my good friend Gemini generate the world's best press release, was totally based on vaporware. So if we can redesign the laws of physics, we can get perpetual dawn. Or we can talk about products that actually exist, and since I'm from Solidime, this is the shameless plug for the world's largest shipping SSD and the solutions that we've been putting together with one of our partners, Dell.
When I originally put this slide together, we actually had the Amazon ad showing you that you could purchase one of these on Amazon and stuff.
I didn't like the price tag.
No, the price, there's a little bit of sticker shock there, but...
Well, it was an Amazon price tag. It wasn't a Solidime price tag.
Exactly, so. Yes. But it was a way of demonstrating that you could go off and buy this thing today.
Yeah, exactly. And I promise this is a good starter. We're getting to the point. I promise it's a developer conference. We'll get there. So purchasing decisions do get made on bad math. This is a simple, CapEx, OpEx over 5 years. If you're the purchasing guy, you're told to spend as little as possible. If you're operational guy, you're told to maximize efficiency as much as possible. And the two don't tend to talk as much as they need to. And so we spend a lot of time talking to customers, with partners, working with companies like Ignition to find a way to show people the net value of what they're looking for that really satisfies the problem that they're trying to solve. Because dollar per gigabyte just doesn't help us out very much. In fact, we should be talking dollars per terabyte anymore with the size of these products that we're dealing with and the relevant cost to the rest of the ecosystem and the architecture around it, because even when we talk about how, quote, expensive these products are, they're still nothing in comparison to the rest of the ecosystem you're plugging them into when it comes to the GPUs, the racks, the power, the cooling, everything like that. And as you can see, data center power is causing a lot of strife. I think actually, in my opinion, data was the new gold a few years ago. I think power right now is kind of the new gold because people just can't get enough of it. I met a gentleman at an event last week, and he has land and he has power, and he thought he didn't have any money to be able to build a data center. I'm like, it's not that big of a problem for you. Here's a few people you need to go talk to that will consume that for you in a heartbeat. So we do have TCO. We have done TCO. We continue to do TCO. We all love it. In fact, there's a session, a BOF tonight, led by a good friend of mine, J.M. Hands, and my former CEO, Nader Salesi, about the next generation of SNIA TCO models. So if you want to come and join that session tonight at 8 o'clock, please do. But we have all these different metrics that we put into TCO models, and a lot of them tend to be very static. They're very focused around, to Andy's point, an IOP, a gigabyte, a terabyte, and they take into account some aspects of system like a server cost. But again, these are all fixed data points, and they don't always solve the problem that we're looking for. And sometimes they can actually be worse than when you're talking with an AI algorithm where you don't get the right answer, you actually get a very wrong answer because the inputs and the outputs tend to conflict. And so how do we get beyond that? We have to start thinking a little more depth around those solutions and how to get there. And so part of that is the next slide, we have updated.
Well,
go ahead.
Before you move off that, one of the things I did want to point out is that this model takes into account a lot more factors than just the power and cooling. It takes into account the idea of disposal, of the replacement costs, of the maintenance costs. They've even, this model even calculates in greenhouse gas costs if that's actually something that you're going to pay attention to.
Yeah. And what we've done is, if you look at the existing SNIA model, it's got a lot of very good static inputs, but it's getting to the idea of how many different inputs are acceptable, successful, and if the static number versus the ability to be dynamic with it is more important. And we've noticed the more dynamic you can be with that and the more options you can provide, whether the consumer of that wants to use them or not, that's a conversation that I and that customer or yourselves might want to have about which things are the most valuable for you when you do those calculations. But at the same time, adding more is never necessarily a bad thing as long as you add them in the right way. You don't want to add too many options, again, because then you could skew results in an even more negative way. So when you take a look at some case views of it, when you're talking about different usage models, different inputs of this calculator, you can see you have a base case. You can do a low case, a high case, in this case, the cloud storage provider solution, but all of it can be input and show the value or input-output concerns that people have. And you can see the OpEx bars, as far as the red, tend to skew a lot of it when it comes to the difference between a CapEx and an OpEx. And that's very important to realize when you're trying to look at a long term. And now that we're getting even beyond the 5-year lifetime of products, we're starting to do 7 years and even redeployment after 5 to the next 5 years in a different workload. These types of numbers come into a lot more value when you look at the cases in the different use models. And even these...
Just a quick explanation since you kind of glossed over this, but the 3 columns are showing a hard drive-based system that has SLC flash, SLC cache in front of it, as opposed to the other 2 that are monolithic QLC systems.
Yep.
I just want to make sure that we have understood what we were looking at.
Of course. Yeah, and so that's again showing that there are ways that these different solutions can bring value. And again, this is using the existing solutions. We're going to start working towards the path of showing you some of the cool new ideas that we've put together working as a collaborative team. So
yes, and so this is, I'll get into some of the interesting things here. There's an awful lot of, one of the next things that you're doing wrong is basing your hardware buying decision on hardware specs and benchmarks. There's the requirements of your applications, the requirements of your business workload, these are the things that you need to pay attention to, and then size your systems appropriately to handle that. If you're just going off and buying hardware to fill your data center and then expect that you're going to load up your applications on it and have it all work properly, you're doing it backwards. You should actually be speccing this stuff out ahead of time. One of the things that's really important is to think about is that you are not running benchmarks as your business case. So benchmarks might be cool, but they might be sexy. They might show you all sorts of interesting things. They might show you some characteristics where you can compare things one to another. But benchmarks aren't actually modeling your business case, and lots of times benchmarks do not show you the contention cases that you would be running into in your actual business cases. They don't show you potentially multiple workloads running in the same data center. Those are all things that you should be paying attention to. And I hate to break it to you, but lots of times hardware is specifically tuned to run benchmarks very well. So,
Yeah, one of the things we run into, especially as a hardware storage provider, is I get my engineering team saying, what do you want it to do? And I say, well, it needs to do X in Y benchmark. And they're like, okay, that's easy, it's a benchmark. But then you go to the customer and you say, well, here's the benchmark we ran, and it said, doesn't look anything like my workload. How do you know that's even going to be valuable to me? So then I go and say, okay, engineers, go run this workload. Like, how do I emulate that? I don't even know what that means. So we run into that software-hardware contention problem with anything that you do around a lot of these cases. And that's one of the things we're working on trying to solve together.
Yeah, and in case you think I'm kidding about hardware often being tuned to match performance, this is a perfect example of it. How many people remember the Volkswagen TDI scandal from 10 years ago? Yeah.
I got a couple.
Okay, so yes, this is a perfect example of tuning the hardware to match the benchmark. And I am going to say something up here that probably my former employer at the time doesn't want me to say, but we specifically tuned storage stacks to run benchmarks. And it got to the point where in one case, we actually set stuff up to recognize if we were running a certain TCP benchmark, we turned all the locking off because we knew what the results that were going to get spit out were going to be, and damn if we didn't have a good TPC result.
Yeah, and another aspect of that, since he's brought the car up, and we'll throw a quick segue in here, the Ford Probe is a perfect example where even hardware doesn't talk to hardware. The original Ford Probe, if you go back and look at the 80s version of the car, had two little divots in this nice metal hood for some plastic strut extensions, because the guy that designed the hood profile had to have it perfect, but he didn't take into account what the strut size was. So they actually literally had to cut holes out and put in plastic things that decided to fade very, very fast and ugly. That's another good example, even where hardware doesn't talk to hardware, let alone getting into workloads.
And this is, again, moving off of the car analogy, but one of the things that you'll run into is if you're going off and buying systems from a particular vendor, you're always going to be you're always going to end up buying excess resources of some sort because they're going to sell you a complete system, and it's going to have all sorts of things that you want to use and you'll need to use, and then it's going to have all sorts of extra things. And if the things it has are in too short a supply, you're going to end up buying more of it, which means you're going to end up with more excess of the things you don't need, and it's going to be, you're going to run into additional problems with that. Lots of times, you're not paying attention to what your software is actually doing. So this is something that I learned recently, that the common LLM models that you can currently get, that you can just download as LLM models, are incapable of saturating GPUs. That the software is written in such a way that the LLM model is not capable of saturating the GPU and keeping it busy. So whoever's been working on those hasn't taken the time to actually design the software properly to be able to pipeline the GPU load out of it to make best use of the GPUs you have available. NVIDIA probably loves this because it allows them to sell you more GPUs that are once again only getting used at 30%. And when you're talking about the buying hardware, there's always going to be some bottleneck point, and you can move the bottleneck around. You should work on designing your system so you understand where the bottleneck is, and you should move the bottleneck to the point that is the least obtrusive to the workload that you're trying to get done. But it's a matter of fact on systems that have components and buses and things that interact, that there's going to be some point of contention there, and that's going to end up being the bottleneck. And one of the great examples of how this has been fixed in the past few years is the idea that changing storage interfaces from SATA to NVMe, where SATA typically would have a queue depth of 32 or possibly 64, and NVMe has queue depths more like 64K, and they have numerous different queues. And this allows you to preload the drive more and have more workload going to it. I attended a presentation several months ago where someone tried to spin this the other direction. They said, you know, the workloads from 5 or 10 years ago only need queue depths of 32, whereas these AI workloads that you're doing need workloads of more like 64,000. It's like, you know, that's actually a factor of the hardware that's underlying it, not the workload itself, but they were convinced that they had it right.
And the queue depth does play a lot into it, just because you think about now with NVMe and the queue depths and what our AI partners are looking at doing, how many commands are in a queue and which way do you flip it? Do you have more commands in a single queue, or do you have more queues with fewer commands and all that kind of stuff? So there's a lot of continuous evolving of what's going on here with all of that. And you really have to understand that we're moving at, you know, faster than the speed of light, and we're trailing with the actual results at the speed of sound. And so how do we kind of keep those things aligned and make sure we're understanding what's next and how to forecast both in hardware, software, and the consumption of those through TCO?
Yeah, and this is especially important for an awful lot of very dense SSD models, such as what Solidigm is selling, because the SSD itself is actually laid out as a bunch of chiplets. And if you actually have a queue that you can fill up on it, the chiplets have a set bandwidth, but you can potentially be running multiple chiplets at the same time if you actually have a deep enough queue of commands to be able to do it in parallel.
And that's where you get a some-way software guy talking about hardware, because it's not really chiplets that we know chiplets from like the chiplet conference, but it's broken down into the array is broken down appropriately to handle that data flow for sure.
Yes. Okay, I'm sorry.
It's all good. I'd love it to be chiplets, to be honest.
If you actually look at the layout of a Solidigm SSD, the QLC cells are individual cells on.
Yeah. There you go.
And it's, you know, this is just, you know, probably repeating what I've already said, but it's hardware vendors are interested in selling you hardware. And if you haven't actually gone off and done your homework and figured out what you need, they're not going to do it for you. They're going to say, oh, this is what you need. Go ahead and buy it. And this is where we get into what you should actually be doing. So system engineering and software engineering should be engineering disciplines. If you take a look at electrical and electronic engineering, they do numerous simulations. They do circuit simulations, they do behavioral simulations, they do heat map simulations, they do all sorts of simulations. They do months and months of simulations before they lay anything out on silicon or anything out on a printed circuit board, because they need to get all this stuff right before they lay out on hardware. Chemical engineering is largely the same way. They will model what the molecules are that they're going to need, or they will, in some cases, they will, like petroleum exploration, will you know, take a look at the models of what characteristics there are when you typically will find oil somewhere underground to be had, or somewhere, you know, in shale or whatever to be had. Mechanical engineering is, of course, one of the biggest uses of simulation, where you simulate the material strengths, you simulate the way things move, you model things so you don't end up with little bumps on the hood of your Ford Probe.
And your plane actually lands on time at San Jose Airport.
Yes. You design things so you know, your aircraft doesn't have a bias to want to fly into the ground straight down, or have its doors blow out on you, or other things. These are things that you should be simulating and designing ahead of time so they don't actually happen in real case. And thankfully, aircraft manufacturers always do it that way, so we never had any of those problems I just mentioned. And then the civil engineering, structural engineering is, you know, largely the same way.
Yep. And in the case of a certain Lionsgate Bridge in Vancouver that I recently had the joy of driving under in a boat, it was built by beer. I see the eyes in the room. So actually, Guinness Beer needed a way of getting their beer from one side of the city to the other, and they decided to buy a bridge built by beer and then sell it back to the city for a profit. because they were able to go through and do all the math and all the TCO on how to build a bridge and ensure that their beer could cover it and the city would actually buy it back.
Okay, and there you are. There was an engineering effort that went into building the bridge built by beer. And there's also bioengineering, where there's all sorts of things about sequencing genes, pharmaceuticals. Pharmaceutical companies build out their organic molecules and come up with what they think is going to be the right drug to make something work. Maybe like figuring out the way to immunize against certain immunize against certain viruses is one of the things that is going on in bioengineering. None of this simulation, none of this work goes into what's being done for software engineering and system engineering. You do this stuff because it allows you to come up with answers cheaper, faster, and more flexibly than you would have if you just tried to experiment and come up with what you need. Isn't it about time that these engineering fields of system engineering and software engineering start taking the same approach of doing simulations to figure out what you actually need before you actually go off and build it? And this is where Magnition comes in, where Magnition is particularly adept at figuring out doing cache tier sizing and this type of thing, where if you have an application that you're running and you are trying to speed it up, and if you throw some cache at it, in this case, you can see that we threw some cache at this, whatever it is, and the latency improved some. But if you throw twice as much cache at it, or even 4 times as much cache at it, or even 8 times as much cache, you really haven't seen much more improvement out of it. So the idea that you can add more cache and get the same type of improvement is mistaken. And you can do this experimentally. You can go off and you can build a system and it's like, okay, it's not running fast enough. Let's throw more memory at it. Lots of people already do this. And at the end of the day, you end up throwing loads of memory at it and not actually getting much improvement out of it. And it's for this exact reason. And if you simulate it and figured this out ahead of time, if you actually ran the workload in a simulator and then simulated the amount of cache that you would need, you could figure this out. This graph that we've shown here out of a simulation is invisible if you just do the experiment. You're blind, you can't actually know what this graph is until you've done all the experiments. However, if you simulate the problem ahead of time, you can come up and say, okay, I'm not gonna spend 8 times the amount on cache just to get this little bit of improvement. If I really need that much more improvement, I need to either re-architect the system or come up with much more cache to it. And we apply the same sort of thinking to multi-tier caches as well, where you can come up with what are the sweet spots that actually have multiple tiers of cache and what is the best way to take advantage of it, where you don't oversize one cache or undersize another, you have the right size buses between them. And this is really, as I said, really a sweet spot for what Magnition does, but we do general purpose, large scale simulations. And let me get into, this is why we're here at a storage developer conference, where we actually will build out large scale simulations. We build behavioral simulations of a complex system by doing a behavioral model of each one of the components and interconnecting them. And we end up with, we end up with repeatable results out of this, where the behavioral model will come up with the same results every time. So no matter how you build out the system, changing the configuration is what's going to change the output, not just trying to run it again.
So as the hardware guy on the stage next to the guy with the code on the screen, how do I and you get along well enough to be able to understand how to play with this appropriately and solve our problems?
Scott, this is a storage developer conference.
Some of us are hardware in the room.
But it's like, if you can't read code,
yeah.
Okay, but anyway, we do actually have graphical representations that can come out of this, where once the code is written, once the simulation is written, and this is an eye chart. You're not supposed to be able to read all of it, but the idea is that these are various different components, and this is a flow graph of the various different parts in it. And the cool thing that we have is that you can drill down into any one of these and see the additional components inside of it, and or expand out and see the larger thing. And this right here is actually a representation for a simulator for content delivery network, because we've been working with Solidigm for about a month now, but we really haven't built out the large-scale simulation with Solidigm yet. We're in the process of doing that. Tune in for another conference soon. And then the way we make this, yes? That's a good question, and we will get to that. So the input, if you want, the input can be synthetic input. You can put whatever you want into it. But the real value in what Magnition does is that we will build replayers for applications. So you can actually, you can attach an application to it, and you're not going to get results out of the application, but as long as the application can run against the simulation, you will get timing and performance, and in our case, cost results out of it as well.
So for us in the work model that we're doing, is a lot of it is the capacity, performance characteristics of the devices themselves that go beyond just the speeds and feeds, but add into the rest of the variables in the configuration.
So in the case of Solidigm, it's easy. We're going to be using storage I/O traces to run against what's the simulation that we put together. And again, this is not intended to be readable. It's just an eye chart, but it's the idea that we actually can build many, many variables into each one of the components, and you can model, you can change the variables in these, so you actually are changing the behavioral model a little bit just by changing some of the variables. And this gets broken out into a fairly easy to edit format, and we also have an editor that you can use. But in this case, there's a bunch of different variables in here, and you can create ranges of those variables. Here you can see a couple of things that have ranges in them, where we've come up with different cache algorithms. We've come up with different number of servers. And the other thing that I will come back to when I show this is using the exact same simulator to simulate two very different workloads. And we'll get to that in a few. But the whole idea is that there's numerous inputs here, and what we end up with is millions of bits of output that we can actually look at that point and categorize appropriately.
So we can run one specific storage test in our platform, fish those variables and those inputs into this platform, and then completely simulate every possible iteration around that.
Right, and the whole idea is that I get into this in a little bit more detail as well, but it's like start off with a manageable number of variables, and this is exactly what we did with our Solidigm test, where the only thing that we really varied was the duty cycle. And our very first experiment was let's vary the duty cycle of the various different drives that are in here and see how that affects it. And the reason we varied the duty cycle is instead of paying attention to CapEx, we're paying attention to the total cost of ownership. And if you take a look, one of the biggest numbers that's different here is the idle versus active power of both hard drives on the left and SSDs on the right, where the duty cycle should make a big difference in how much power these things actually consume, which would also be a matter of how much cooling they consume. And it's like, this should be a big lever that we should be able to graph out and see big results. And the end result of this is across the x-axis of this, the duty cycle really isn't the overbearing factor in how much these things cost. You can see that there's a very slight upward tick to all of the various different graphs, but the duty cycle of the drives is not the factor that's the biggest in what causes these costs to increase. So we figured that we were going to come up with an impressive graph to show you guys, and it's like, we ended up with an experiment that didn't actually show you a whole lot of interesting stuff. And this is where we get into way too many design decisions are made on too few pieces of data. And this is, the whole idea is that the way that you build your system shouldn't be like a 3-course menu where you get to choose one from each and see which one works the best for you. It's not. It shouldn't be choose one from here, choose one from here, and choose one from here, and see what works best for you. You should be able to come up with much more options. And you think that I'm just kidding with a 3-course menu, but I hate to pick on HPE because HPE does some really good stuff. But here is HPE's AI offerings. These are their AI server offerings, and that's what they have. They have a 4-column chart that shows the various different things. And if I'm going to be picking on our friends more, I'm going to pick on Solidigm here for a second and say Solidigm put together a really nice TCO model, but they really didn't change that many variables in it. So the stuff in green are the only things that they really changed a whole lot to put together the models for those 4 things that Scott showed you the graphs of earlier, and that's the low, base, high, and cloud service provider use that were discussed. And I'm sure they ran other experiments as well, but they did not end up with the vast array of experiments that we did. And in fact, one of the things that we added on later on, this is what I showed you earlier, which was just using duty cycle. And we added in a couple other things here. We changed the duration, the life cycle of the deployment term. And this just shows hard drive deployment term, but we did the same for the SSD deployment term as well. And we ended up with a slightly more interesting graph where there's a little bit more variance. And this one's kind of interesting where you can actually see the crossover as we get to cheaper and cheaper hardware. In this case, starting with the most expensive and coming down to the least expensive hardware here. And this is a case where you should go off and you should be taking the information you get and say, okay, that's not nearly as valuable as something else. Let's start looking around. And this is why we have the ability to change so many different variables. The idea that you can build things in various different ways and experiment with different things and find out what's actually valuable to you.
And as part of this is, as we're going through it, we take our existing TCO model, as you see here, and we're able to expand upon it and take products and solutions that were designed for a very specific use case and expand that footprint appropriately to other things. So like, for example, we demonstrate a CSP workload in this. We can now say, okay, I want to take a similar workload, but I want to put it at the edge with different constraints. And can I run that same workload at the edge in the same type of an environment, and what does that look like without having to actually go build it? And that's one of the things that we can start to do with these kinds of simulations, is we can start playing with all the different variables in a much more emphatic and important way to support the customer base and listen to what they have to say, put it in there, show them a result, and then we can go build a solution together and make sure it works.
It's almost like I had another slide ready to talk about the TCO cost. And one of the things that's important here is when Solidigm put this together, they came up with numbers for each one of these categories, and they didn't move them around a whole lot. They simply came up with numbers that made sense. And this is one of those things where, depending on where you are, these numbers might vary quite a bit. If you're running a data center on Hawaii, the cost of electricity, the cost of shipping, the cost of maintenance probably is going to be a lot higher than it is if you're running one in Redmond, Washington. So these numbers are things that can become variables in our simulation now. We can actually twist the knobs to run for your workload, Mr. Customer, rather than us just coming up with, hey, here's some really cool numbers that you can look at. And this is where we get into, we have the rich sets of data, and these are various different plots from our content delivery network where we're comparing various different things. And again, the things we're comparing here are, average round trip time, average hit rate. These are various different things that we were playing with when we were doing large-scale content delivery networks. And we end up with a bunch of graphs. And the thing is that some of these might just look like they're lines of things, but if you actually fit curves to them, you can actually see that there's things that just appear to be lines in some cases actually do have a curve that you can fit in there. And it's like, okay, these are things that actually make a difference, and we can see some cliff characteristics like on these bottom two, or some ledge characteristics where things even out. And this is information that you can use to actually further refine your model.
And the ability to have this kind of an output in real time by way of the simulation work and things like that, and putting the real world inputs into it, but being able to see what it can do over time and scale, you do get to see beyond those points where you can no longer design it into it, right? So a rack has a certain limitation, and we can only fill it out the way we know how to do it, or way a specific customer does. But if we can start marrying all those data points together and putting them into a tool set that allows us to just completely tailor exactly what you're looking for, we'll get sets of curves that even our customers don't realize that there's an opportunity at some point to make a minor change and drive significant value to the system.
And this information, while it's certainly valuable to Solidigm themselves, this information at the end of the day is going to be far more valuable to Solidigm's customers, who it's like, I'm using it for this application. Let's figure out how to best use your equipment and put it into a system that makes the most sense. And this way you end up with the ability to right-size things. You should be doing this before you go off and purchase things. It's another vendor that we talked to previously. We talked to them about this idea, and they said, well, we need to go off and buy the hardware first. And it's like, no, you're not listening to us. We actually need to design what types of hardware we need before you go off and buy it. And they were in the middle of a purchasing cycle, so it's like, let's go spend the money now, and then we'll figure out how we're going to use it later. But you don't end up with a clown car full of too many clowns.
And this is becoming even more relevant as we move forward, because the AI bubble, right? We've all been doing this, and we know that at some point it's going to have to plateau and kind of solidify and centralize back down. And being able to be ahead of that curve and helping you as our customers, our partners, and just the industry understand a better way to map all that data out allows us to react much more efficiently.
And this brings us to our next point of decisions are made without taking applications into account. So we've talked about this to some extent already, just attempting to run things on benchmarks rather than trying to figure out what the various different pieces are. But the max performance of each component doesn't define what you're going to end up with. And very few benchmarks actually measure the actual performance of applications. There's a benchmark running around called MLPerf that's out there. And MLPerf is an interesting benchmark, but at the end of the day, it really doesn't measure the same thing that an AI.
But I scored a #1. I was best in class on MLPerf.
Congratulations. You win absolutely nothing.
Yeah, exactly.
And the biggest thing is that if you just run one benchmark, you haven't run a mix of workloads. You don't have any idea what it's going to look like when you run a bunch of things. And nobody goes off and buys hardware to run one specific thing, unless
that's your only market.
That's your only market. And here's a perfect example that I presented last year on this, where I talked about CXL last year, and in this case, we ran with the idea that you had a system that had 2 banks of CXL on it and 1 local set of DRAM on it. And in the first set of examples, we just said, allocate memory as you want and run the applications in any arbitrary order and see what happens. And in this case, you can see that if we just ran one application, it took 50 seconds to run, and the average latency was, I don't know, somewhere around 30 milliseconds, or 30 it shouldn't be 30 nanoseconds, it is. And if you ran 2 applications, it took a little bit longer, and the latency went up a little bit. And if you ran all 3 applications together, it ended up taking, all 3 of them together ended up taking more time, and your average latency had continued to go up.
And
however,
go ahead.
However, when we ran the same experiment and pinned each one of the applications to their own NUMA node, so we knew exactly what was going on, all 3 of the applications, whether they were running together or running independently, all ran in the exact same amount of time. And the latency for each set of applications was exactly the same as well, where and if you take a look at the first graph, you can see that when the difference between running one application and running two, the latency goes up for that first application. And in the second case, the latency stays exactly the same between running one, running two, or running three cases of that, because we've pinned it to a particular NUMA node. And we were able to end up with numbers that made sense. And again, I apologize, these numbers are really small here, but I tried to blow them up here for you, just showing that this was 50 seconds of runtime versus 80 seconds of runtime, and 250 nanoseconds average latency for the worst case, but only 50 for the best case as well.
And so as we're working together, we're going to be able to present soon very similar examples of this, but based instead of specifically in this particular use case around the storage products, whether it be the high performance cache drives or the high capacity drives. We'll be able to showcase where the workloads align to these different SSDs and how they work better. And again, all through simulation without having to build expensive hardware platforms or taking the time to build out those platforms, which is another aspect of it. You get faster time to results. And
there's various, what I want to show is that we can actually optimize various different workloads, or various different, we can optimize different systems for different workloads in different ways. And this is part of what I was trying to show with the comparison of the Wiki versus Cloudflare content delivery networks, where we took the exact same simulation model, the exact same model framework, and we changed the variables to make them perform better for each one of those cases. And the whole, one of the things that we really want to do with Solidon is talk about the idea that this is a multi-objective optimization. We're not trying to optimize for performance. We're not trying to optimize for cost. We're trying to come up with a set of objectives and end up with the right balance for these various different objectives to come up with what makes sense for the customer who is using it. This makes a big difference if we actually look at the idea of total cost of ownership versus CapEx, where the stuff that we've done for the content delivery network cost was simply CapEx. It was the amount of money that you would spend up front to do this. And this also allows you to figure in the time factor as well, where there might be some game playing that you play between the CapEx and OpEx, where it's if you're on a tight budget now, but you expect that once your business starts taking off and you start making money, it might be that you're going to skimp on your CapEx now with the expectation that your OpEx is going to be higher later on. Whereas if you're someplace like a university project, it might be that your project is funded up front, and then the results of it, that you're not necessarily going to get funded to continue to run the thing forever, so you need to be careful about how you spend that money. So this is another part of the game that you can simulate and figure out what's the best way to spend the money I have and get the performance I need out of it. So you can play with some of these numbers.
And at the end of the day, it also offers the opportunity to look at the competitive nature of things too, right? So we've shown a couple of graphs that highlighted the difference between a hard drive and an SSD, and we're in that era now where everybody's trying to say we're trying to kill off the SSD or the hard drive with the SSD, and so there's opportunity to actually see if that math works out in some cases with how some of this simulation work can go. And again, that doesn't require me to go build racks and racks of hard drives and wait for one to fail to know the failure rate. I input a failure rate for one versus the other, or I input a performance characteristic, to his point earlier, active power versus idle power. We can actually start looking and seeing for a given workload, maybe the hard drive is dead for that workload versus the solid state drive, and be able to show that math in a more real time and not have all the fun buzz that comes out everybody every time somebody puts out a press article about the death of this or the winner of that type of thing, but actually back it up with engineering data.
And here we are with our engineering data to back that up. So this is the case that we built out for the content delivery networks. I talked about this at the regional SDC earlier this year in Denver. You can go look up the presentation or online at this point. But we took Wikimedia, which is a particular type of content delivery network, and we built out a bunch of different configurations to run. The red dot was using Wikimedia's algorithms and Wikimedia's input chain, and that is that is exactly the performance that we got on essentially cache hits. With a CDN, it's important you want a cache hit because if you miss the cache, you have to go back to the origin, and that ends up possibly being several seconds. Think about trying to look up a 2-year-old SDC video. YouTube is going to take almost a minute to get it to you because it's not in the cache anywhere. And you can see that in Wikimedia's case, Wikimedia probably didn't optimize their things a whole lot because these big blue bars show the experimentation space that we ran against the Wikimedia, just changing the algorithms, changing the configuration. And this represents about 300,000 runs, these blue bars. So we ran about 300,000 different simulations, and these are the breadth of our experimentation space with those 300,000. By contrast, we did the exact same thing with Cloudflare. Cloudflare doesn't publish this stuff, but we worked under NDA with Cloudflare to get their CDN algorithms and their CDN traces to come up with how things work for Cloudflare. And the big red dot represents what their baseline is. That is exactly what Cloudflare performance would be. And you can see that they've actually optimized it quite a bit because we ran about 600,000 experiments on each one of these. And this is the experimentation space that we got. And you can see that even our median, the black line in the blues, is not as good as their baseline. So Cloudflare, obviously being a for-pay content delivery network, took advantage of this. So this is one objective. We also looked at an idea of multi-objective, where we said, okay, let's look at both performance and cost with both Wikimedia and Cloudflare. And the dashed lines are the baseline. So the cost is just a normalized cost. And you can see that if we went for best performance, we got way better performance than Wikimedia at a slightly higher cost. If we went for minimum cost, we ended up with a way lower cost, but our performance was way worse than their baseline. And we had an intern working on this, and she had a particular research case in mind. So she applied her research case, which is the third bar here. And you can say in this case, we did slightly better than the baseline. We did slightly better than just the best performance in terms of cost, but not quite as well in terms of performance. And with Cloudflare, you can see that it's what we ended up optimizing quite a bit with Cloudflare was we got the cost way down in our research case without hurting the performance much at all. So this was an example of things that we fed back to Cloudflare and say, here with our experiment, this is what we got.
And so as we move forward with the solid state drives, we're going to be able to start doing this for those types of workloads, the end customer need workloads, like, for example, local cache versus remote storage, and the east, west, north, south, all that stuff that's coming out as hot topics in the AI ecosystem. We're going to be able to forecast the opportunity to best utilize that solution, whether it be with a specific OEM or a specific configuration, or how do we optimize the DRAM footprint versus the HBM footprint versus the SSD footprint, and what are the trade-offs we're willing to make?
Okay, and in this case, you can also go into these sets of data and say, okay, my objective is this, so let's actually take these sets of data and work on optimizing for this particular thing and come up with whatever your objective is, or some combination of them to blend them. And now this is largely what we came to talk to you about. We will be talking to you about this more with hopefully much more rich graphs and data from Solidigm experiments on real world workloads, and we will tell you what those workloads are when we do those demonstrations, so you actually have some idea of what we're testing and that we're not feeding you a line of crap.
Let's just say the SSDs weren't the slowest problem here. There's something that spins around a little bit that caused delays in the data.
Yeah. And so hopefully you learned a little bit today. And we strove for the last item in particular. Maybe this wasn't as interesting as looking at your phone, but we tried to get there.
So at the end of the day, when you're talking about TCO, just realize that there are way more opportunities to drive successful conclusion. And when it comes to partnerships and working together on things and not just trying to stay isolated in your little spots. I can say a lot about what I can do with AI, but if I don't work with my partners, with my customers, with even the industry, for example, within SNIA as a board member and a technical work group member, we need the ability to give the market the faster access to the data that they're looking for. And this is one of the paths that we see as a successful way of doing that, is through simulation of taking a known good data set, expanding upon it very quickly, easily, and then adjusting appropriately.
Okay, questions?
We've stunned them into silence.
Oh, yes.
When working with traces, how are you dealing with time? Like, when we run simulations, one of our biggest bottlenecks is just the single-threaded nature of having to order events to decide.
Yes, and
like working on capture mixture algorithm.
yes, and then this is actually one of the things that we run into, and if we're purely running with traces, we do run into this where we're stuck with the idea of the sequence of events is what the trace says the sequence of events is. So one of the things that we actually try to do are build harnesses to allow you to run applications against our simulations. And the key thing to actually being able to do this is that the application has to be allowed to throw out the results, because if we actually have to do all the calculations, the simulation will end up taking more time than actually running it. And the whole point of this is that we're trying to simulate things quickly and come up with the answers as much as possible. The other thing that we have played with to some success, but not a lot, is to separate the request from response portions of the trace and just play the requests in and potentially intermix the responses in at a different rate and see if it changes it a whole lot. But that still hides the lockstep nature of the request and response, which is often the case. So it's a tricky problem, but more often than not, when we're doing this, we're trying to come up with a harness that will actually
I've upped it too much.
That will actually take care of it. Okay.
Yeah. Well, time is up, so we do appreciate your time.
So yeah, thank
we don't
you
want
for
to keep
attending.
you from lunch. Thank you for attending, and if you have more questions, find us. We'll be happy to talk.
Yes, absolutely.